Okay, so we can start today's session with Boris Pioline from Paris.
Thank you. Can you hear me well? Good. So I've been asked to review some recent developments on black holes and topological strings, and I'm glad and honored to do so. However, it's a somewhat risky business since I was not directly involved in the most recent developments, and moreover, many of the experts are in the room, so I'll try to do my best. So I think we all agree that explaining the microscopic origin of the Bekenstein-Hawking entropy of black holes is a pass-or-fail test for any theory of quantum gravity. And of course, string theory has been tremendously successful in passing this test, at least for a class of BPS or near BPS black holes, and in the limit of large charge. Now, recently, especially in the context of n equals 4 and n equals 8 black holes, it has been possible to go much beyond this large charge regime. And in fact, now it has been proved that the exact microscopic degeneracies at any finite charge are encoded as certain Fourier coefficients of modular forms, realizing a prophecy of Digraph, Verlinde, and Verlinde in 1996. And so the goal of my talk will be to review some attempts at trying to reach the same level of accuracy for BPS black holes in n equal 2 string theories. Now, this might sound a little academic, but from previous experience, we know that asking such detailed questions is very likely to uncover new results in mathematics. And if we're lucky, maybe we'll also learn some general lessons about quantum gravity. So here's the plan of the talk. I'll start by reminding you of the setup and some of the very well-known facts, in particular the Augury-Strominger-Weffer conjecture. I'll then move on to describe multi-centered solutions and issues of lines of marginal stability in n equal 2 supergravity, which was at the heart of the recent progress. I'll spend some time reviewing this MSW superconformal field theory, which is still until now, I think, our best handle on the microscopic derivation, microscopic understanding of the dynamics of n equal 2 black holes. And then I'll mention some new results about systems with D6, 1 unit of D6 branch charge, which can be counted using a symplectic invariance, Donaldson-Thomas invariance, although there isn't really such a good microscopic understanding of them. Now, this will provide the main ingredients for a recent proof of the OSV formula, which I won't go through the proof, but I will tell you what the assumptions are and what the amendments are. And I'll end with some, I think, very interesting new line of thought, which is to try and think about four-dimensional black holes. Well, try to relate four-dimensional black holes and three-dimensional instantons, which I think gives a very precise formulation of the problem of black hole counting. So the beginning will be very basic. We're interested in type 2 string theory compactified on the Calabi-Yau threefold. I'll take type 2A to be specific. So this is n equal 2 supergravity. The moduli space splits into a product of the moduli space for vector multiplets and for hypermultiplets. The first factor describes the Kähler structure and B field on X, whereas the second factor describes the complex structure on X, as well as the Raman-Raman scalars and the axiodilaton. So for most of the talk, we can forget about this hypermultiplet part, but it will become very important towards the end. Now, MV is a special Kähler manifold. This geometry is encoded in some holomorphic function f of xi, the prepotential. The xi are the special coordinates, and the Kähler moduli are the ratio of those. Now, xi is also the lowest component of a chiral superfield, which includes the gauge fields, fi mu nu, and so it also controls the kinetic terms and theta angles of all those gauge fields. Now, in general, if you try to go beyond second order, the leading terms in the low energy expansion, the structure of the action becomes very complicated. But at least a special class of higher derivative interactions can be incorporated in a very nice and compact way by letting this holomorphic function f depend on a new variable w square, which is the Weyl multiplet, whose first component is an auxiliary field related to the graviphoton, And then comes the Riemann tensor. So if you integrate such a function on the chiral half of the superspace, then you reproduce the three-level action, the two-derivative action, but also an infinite series of high derivative corrections of R² type. Now, the connection to topological strings is very well known, and is the fact that those coefficients fg of xi are in fact given by the topological string amplitude at genus G in the so-called A model on X. Now, there are actually some subtleties here having to do with holomorphic anomalies, but I will disregard them throughout the talk. So the answer is very well known. In the large volume limit, the prepotential has this classical part, which is related to the intersection numbers on your Calabi-Yau. There is a linear term proportional to the second Chern classes, and this comes from a one-loop effect, one-loop R² corrections. And then there is an infinite series of Wirtschit instantons, which are suppressed at large volume, and whose coefficients are famous mathematically and known as the Gromov-Witten invariants. Now, type 2A string theory on X is the same as M theory on X cross S1. The volume in 11-dimensional Planck units is the dilaton in 4 dimensions, and I told you this is a hyper, so you can tune it the way you want. But the volume in string units is, in fact, a vector proportional to the cube of these Kähler moduli. And so, if you let the imaginary part, where the Kähler classes go to infinity, all of them at the same rate, then this is the same as decompactifying the 11th dimension, and therefore you wash out all the Wirtschit instantons and you get back to 5-dimensional supergravity with moduli space is this cubic hypersurface. But still, you can, from this 5-dimensional point of view, you can recover this infinite series of Gromov-Witten corrections by this famous argument of Gopakumar and Werfer, namely from one-loop contributions of M2 branes wrapped on the cycles, 2 cycles in the Calabi-Yau in a self-dual graviphoton background. So if you do a one-loop Schwinger type of computation and you take into account the spin of those M2 branes, then you do reproduce this infinite series. However, these Gromov-Witten invariants have been reshuffled in these numbers n beta g, which count the number of complex curves. So those are integer numbers in contrast to those. And so they count the number of complex curves with a certain spin, so-called Lefschetz spin G. Now, the objects of interest in this theory are the BPS states. So they're labeled by their conserved electric charges, P magnetic, Q electric, the angular momentum J² and J3. And the mass is, of course, related to the central charge of the unequal 2 theory. And so the whole interest of the game is to determine the degeneracies of these BPS states in a sector of fixed charges PQJ, and importantly also for a given value of the moduli, of the Kähler moduli at infinity. Now, no one knows to do this computation, but much progress has been done by considering instead an index quantity, the so-called helicity supertrace, which is a trace of -1 to the fermion number times J3². This allows to soak up the fermionic zero modes, which are always present. And well, this is a nice and robust quantity, which is locally constant, but still it's not it's not everywhere constant, and it can jump on lines of marginal stability, and this will play an important role later. So at the level of supergravity, it's very easy to construct such BPS solutions, been known for a long time. If you look at spherically symmetric ansatz of that type, where U is a function of the radial distance R, and the Ti are also assumed to depend on R as well, then the radial evolution of those scalars is governed by this Hamiltonian. So it has a kinetic term, and the potential, which is the so-called black hole potential related to the central charge. And the important fact is that this potential is unbounded from below. Now, we're especially interested in extremal black holes in these theories. And if you don't make any assumption about supersymmetry, those are really non-generic solutions. If you want to have an ADS2 cross S2 throat, you actually need to to fine-tune your initial conditions so that you reach the top of that potential with zero velocity. And so those are very non-generic states, and there's been a lot of interest in those recently, which I won't have time to talk about. But I'm going to focus on BPS states. And in this case, we have to look for supersymmetric solutions of the system. This H is really the bosonic part of a supersymmetric quantum mechanics. And in fact, one very nice way to uncover the supersymmetry structure of the system is to lift the motion on this, in this potential to the geodesic motion on a bigger space, which turns out to be the three-dimensional vector moduli space. This is something which I've discussed in several papers with Gunadi, Nainsky, and Waldron. And it's quite a useful device. But anyway, whichever way you find the supersymmetric constraints, they take the form of these first-order differential equations, so-called attractive flow equations. Now let me point out that, in fact, those equations can be solved in full generality. I wrote down the answer here, and it will be useful when I turn to spherically symmetric solutions. So these attractive flow equations are first order, and they are gradient flow equations for the log of the central charge Z. So that means that Z in modulus decreases monotonically from infinity to the origin. And therefore, moduli are going to be attracted to the points which minimize this absolute value of Z locally. So that means that the values at the horizon are very robust, and they are locally independent of the moduli at infinity. I've drawn here a picture of such attractive flows, all ending up at the same point. But in general, you might expect to have different basins of attraction. Now, depending whether the central charge at the attractive point, sorry, there's something wrong here. Depending whether it is zero or not, you may have a smooth solution. So if it's non-zero, you have indeed a smooth BPS black hole with ADS2 cross S2 throat. And the moduli at the horizon are fixed by these famous stabilization equations. The Bekenstein-Hawking entropy is also computed in terms of those quantities. But if Z is equal to zero at the attractor point, and if you are in a regular point of the moduli space, then the solution that you construct in this way is nakedly singular, and it must be dismissed. So the question arises, does that mean that BPS states with such charges don't exist? Now, of course, we know that if this is so, we cannot trust anymore the two-derivative approximation. But also an important fact will be the possibility of breaking the spherical symmetry. So what happens if we had the higher derivative corrections? Well, the full solution is very complicated, can be only obtained numerically. It exhibits some non-physical oscillatory behavior from infinity to zero. But this isn't physical because it can be reabsorbed into field definitions of the graviton. But the near horizon geometry, which is what is of interest for computing the entropy, can still obtain explicitly. One way is to use the supersymmetry enhancement at the horizon. And so this was done long ago. Sorry, this should not jump like this. Okay, yeah, so, and the entropy, of course, is no longer given by the Bekenstein-Hawking entropy, but you have to take into account the R-square type of corrections using the prescription of Wald. Now, these days, there's a more efficient way of doing this computation, which is to use the so-called entropy function formalism developed by Sen and then Ross and Larsen and many others. And this is a property which holds for any extremal black hole, be it supersymmetric or not. So the statement is that the Bekenstein-Hawking Wald entropy for such black holes with ADS2 cross S2 throat is just given by the Legendre transform of the entropy function, which is the value of the action on the solution with specified magnetic flux Pi and electric flux phi I. So the phi I are electric potentials conjugate to the QIs. Now, for n equal 2 black holes, including these higher derivative F terms, this entropy function is indeed related to the topological amplitude, so-called topological free energy, the imaginary part of F evaluated at P plus I phi, and also the value tensor has to take a fixed value 2 to the 8, but this is largely conventional. And so this observation has prompted the famous OSV conjecture, which relates the microscopic degeneracies to the modulus square of the topological amplitude. Psi top is e to the if via this Laplace kind of transform. Now, if you take a large charge regime and approximate this integral by a saddle point, then you recover indeed the first, the classical expression. So this was the main motivation for that conjecture. So much of the recent activity in this area has been prompted by trying to answer some of the many questions raised by this conjecture. To what extent are the two sides really well defined? Is this a topological amplitude a formal quantity? Does it, where should we integrate it? What are the contours, etc.? And more importantly also, in what regime of moduli space and charges should it hold? So mentioned it has to be in the large charge regime, but you have to scale all the charges at the same rate, or do you have to do something else? How can it be consistent with the electromagnetic dualities, and especially we know that this duality usually required to introduce holomorphic anomalies. This is a subject that has been much discussed by Cardozo, DeWitt, and collaborators, and in fact 2 days ago there was a paper going further in this line, but unfortunately I don't have time to review it. Is there a physical interpretation to this inner product of wave functions appearing on the left-hand side? This was discussed by Ogori-Vafa and Verlinde in trying to use this, this Hartle-Hawking wave function proposal. Well, can we control the non-perturbative corrections beyond this large charge expansion, etc., etc.? So most of the recent progress, I would say, has been focusing on this second question: in what regime of moduli space and charges should it hold? So this will be most of the subject of the talk. So multi-centered solutions do play an important role in resolving this question. Those are actually quite well known by now. But so if you relax this staticity assumption, you can see that you can actually superpose these single-centered solutions, which I exhibited previously, by replacing the 1 over R by a sum of poles at various locations XA in R3. And this is always the solution provided the locations of the centers satisfy these n-1 constraints. Well, the notation here is that the gamma A is the vector of charges at point A. Gamma infinity is this vector CIDI, which encodes the value of the moduli at infinity. And this inner product is the symplectic product between the two things, so it's antisymmetric. So this solution is not static, it carries angular momentum. Classically, this is a sum over the angular momentum P dot Q for each pair of black hole in this solution. But there might be some extra quantum contribution, and in fact there is. So those are solutions, but are they physical? Well, one should require that U and Ti stay in their own domains of definition, and this is usually very difficult to check. But for two centers solutions, you can be very explicit about it, and you'll discover that the radial distance between the two centers is related to the values of the moduli at infinity by such a formula. Notice that the charges have to be mutually non-local for the solution to exist. An important fact is that the distance diverges when this imaginary part of Z1, Z2 bar goes to 0. That is when Z1 and Z2 have the same phase, well, really modulo 2 pi. And this is where two states, gamma 1 plus gamma, well, gamma can decay into gamma 1 plus gamma 2 at threshold. And of course, this two-centered solution is only going to exist on the side of this line of marginal stability where this quantity is positive. So this is for the two-charge case, but it holds much more generally. Now, if you scan through all the values of x in your spatial slices, then the moduli are going to map a domain in this vector moduli space MV. And near the location of each of the centers, this is going to look very much like this attractive flow, single-centered attractive flow previously. So it's kind of a spiky domain, but it gets flattened in the middle. And a general fact is that this kind of domain split tends to fork on the lines of marginal stability. So it can really be approximated by a sequence of spherically symmetric attractor flows glued at the lines of marginal stability in agreement with the charge conservation. So given the total charge gamma and value of the asymptotic moduli gamma infinity, the question arises as to how many different such trees are going to exist. In principle, there could be an infinite number of them. So Denef and Moore made many numerical investigations of this question, and they came up with a split attractor conjecture, which is that a multi-centered solution satisfying all the requirements exists if and only if the corresponding attractor tree exists, and moreover, the number of such trees is finite. So I think this is a rather well-established and well-supported conjecture, although it is not fully proved. Now, what happens if you cross a line of marginal stability? Well, one expects to lose the BPS states corresponding to this two-centered configuration. Now, if they're very far apart, the number of these states is going to be the states of each of the two centers, but then they also have some kind of orbital degrees of freedom because they have angular momentum. So in fact, if you compute the angular momentum using this formula, and if you allow for a 1/2 unit of a quantum angular momentum, then the formula that you get is, again, this inner product of gamma 1, gamma 2, and there is a sign having to do with the fact that we're dealing with the helicity supertraces. So this has been supported by studies of many examples, and so it has also been extended to more than two centers in this recent work. Now, I think one of the most interesting results recently is this Kontsevich and Zauberman formula. We have given a really far-reaching generalization of this wall-crossing formula, and I'll come to it towards the end of the talk, time permitting. So this concludes the macroscopic part of the talk. We have seen what kind of supergravity solutions exist, and so we'd like to get a handle on their microscopic degeneracies. And so the best description so far is this MSW superconformal field theory. And so this only is available for vanishing the six-branch charge. And it uses the fact that if you have a D4, D2, D0 black hole, well, you can lift it up to 5 dimensions, and it becomes an M5, it becomes a black string wrapping the circle. And the black string is a M5 brane wrapping a 4-cycle in the Calabi-Yau, holomorphic 4-cycle, so it's called a divisor, together with some flux on it, which accounts for the D2 branch charge. And of course, the D0 branch charge is the momentum along the S1. So what is the theory on this black string? Well, you can reduce the 0,2 word volume theory of the 5 brane on P. So that gives some superconformal field theory in 2 dimensions with 0,4 supersymmetry. And semi-classically, you can think of it as a nonlinear sigma model on a certain moduli space, which is somewhat complicated, but it has a center of motion part. It has the moduli space of the divisor inside the Calabi-Yau, and on top of it you have this flux degrees of freedom, which gives a torus bundle over this MP moduli space. And that's still not the end of it. So on top of the cotangent bundle of MP, there is also the torus bundle of rank B2 minus B2 plus. So you have you have B2 minus B2 plus chiral bosons. And so if P is smooth enough, so if it lies inside the Keller cone, then using some topological considerations, you can compute the dimension of this MP. This is directly related to the magnetic charges of the 5 brane. So if you know the dimension of the moduli space, you can compute the central charge. So those are the non-chiral bosons, and those are the chiral ones. You plug it into the Cardi formula. You pay attention to the definition of the level, and indeed you reproduce precisely the Bekenstein-Hawking-Wald entropy. of such black holes, including the one loop R-square corrections, which I remind you was proportional to C2A PA. So this was an early success of this attempt to go beyond the large charge regime. And now I think people are trying to go beyond just this leading correction. I should say that this sigma model picture is only valid when this divisor P is smooth, that is away from the discriminant locus. And in general, when you approach this, you will have the 5-brane will start to self-intersect. You'll have some open membrane instantons. And so it's not understood how those effects can be included, but are certainly very important to understand. Now, if you want to go further from this Cardi formula, one could try to construct an index. So this is the 0,4 elliptic genus, which has been studied a lot recently by these groups. So again, it's a trace -1 to the fermion number, 2 insertions of the fermion number to soak up the 0 modes, Q to the L0 minus C left over 24, Q bar, and some couplings of the, some sources for the electric charges QA. Now this object is a very nice object because invariance on the spectral flow, as well as string dualities, require to be a Jacobi theta function. More precisely, it can be decomposed into a sum of modular forms, H mu, times some Siegel-Narain theta functions, which essentially include the effect of the overall of the center degree of freedom. So there are theta functions for the lattice Lx, which is H2 of x. Notice that the whole fluxes live in H2 of p, which is much bigger than H2 of x, and it contains H2 of x as a sublattice. So in making its decomposition, you need also to add a sum of various possible glue vectors, mu, whose number is very large since it's the determinant of, well, CAB is quadratic is linear in the momentum. Now, a very interesting fact about modular forms is that once you know their polar terms, that is the terms whose corresponding to a negative power of Q in their Fourier expansion, then you can actually reproduce the whole of it by summing the polar part over SL2 images. So what's known as Faraday-Tail expansion in the physics literature, or Poincaré series. And so this has a nice supergravity interpretation as a sum over Euclidean ADS3 geometries. This sum here corresponds to the various fillings of the torus at infinity. And so if you want to determine the large level behavior of the degeneracies, what you need to know are just the polar terms. And in fact, the ones which dominate are the ones closest to the unitarity bound. So the highest value of the level is minus CL over 24, which translates into this bound for this D0 branch charge Q0 hat. So we really want to focus on the states close to this upper bound. Notice that since Q0 hat is positive, if you naively try to apply you compute the entropy associated to them, you get an imaginary number, which is telling you that there are no spherically symmetric black holes corresponding to such charges. So there's been two different prescriptions, discussions in the literature about how to describe these polar states. One in the M-theory setup using, zooming on the near horizon geometry ADS3 cross S2 cross X, and looking at bound states of M2 branes and anti-M2 branes at the north and south pole of the S2, and wrapping some cycle on X star by Gaiotto, Strominger, and Yin. And I think a somewhat better setup, which is under more control, which is just in the original type 2A picture, by viewing these polar states as two-centered solutions with 1 unit of D6 branch charge and -1 unit of D6 branch charge at the two centers. So I'm going to follow the second approach. So how do we count such polar states with 1 unit of D6 branch charge? Well, that's a well-known, there's a well-known answer in mathematics. And so the point is that you can describe these states, these D6, D2, D0 bound states, but what is called ideal sheaves, what that means is you just have to look at U1 instantons in 6-dimensional non-commutative gauge theory with specified chain classes related to the D0, D2 charge. And so this is a well-defined problem mathematically, and the number of such objects is the Donaldson-Thomas invariant, NDT of QA and N. Now, an instanton in a 6-dimensional gauge theory is codimension 4, so it defines a complex surface. So it's not surprising there should be a connection to the Gromov-Witten invariance that we discussed previously. And indeed, there is such a connection. The partition function of Donaldson-Thomas invariance is related to this topological, to the worldsheet instanton part of the topological string, up to this prefactor, which has to do with degenerate contributions. M here is the famous McMahon function. It has come up also in these studies of quantum crystals, etc. So let us combine the relation between Gromov-Witten instantons and BPS invariance with this statement about the partition function of the Donaldson-Thomas invariance. So, well, the formula you get is somewhat scary, but not so much after all. So the focus on the first line is, the second line is invariant under lambda going to minus lambda. Lambda was the parameter conjugate to the D0 brane charge. Sorry, the first line, however, is not. The first factor is really, counts the number of D6, D0 bound states. There's a very simple argument which, taking into account the angular momentum of those objects, which reproduces those. And similarly, the second factor counts D6, bound states of D2, D0s weakly bound around the D6 brane. And so those bound states only exist for specific values of the B field at infinity. So you need the ratio of B over J to be very large. If B was 0, as you well know, there are no D6, D0 bound states, BPS bound states, although there are non-BPS ones. The second line, on the other hand, is what you get when you scale J to infinity, but keeping B finite. So once you have once all those unstable states have decayed, you're left with these so-called core states. And so the kind of heuristic picture of the black hole is that you have a core with a halo of D0 and D2 orbiting around it. Now you can easily introduce D4 branch charge by spectral flow, so that's not much of an issue. This is the picture you get when you lift it to M theory, where you have instead, so the D6 branch charge becomes a Kaluza-Klein monopole with some BMPV black hole at the center, and then you have a bunch of Kaluza-Klein waves, etc. So in particular, if we take this decompactification limit to 5 dimensions, only the core states remain, right? If the circle here is large enough, all those states decay, you're left with the core states. So this gives a relation between 5-dimensional black hole degeneracies and this Donaldson-Thomas invariance. Now, so it's a simple computation if you assume that Q is primitive. And in this way, you recover a well-known, a famous conjecture by Katz, Clem, and Waffa, who related the 5-dimensional black hole degeneracies to the BPS invariance. There's been some very interesting recent work by Huang, Clem, and Marino and Tavanfar trying to check this explicitly on compact Calabi-Yaos. It's a hard game because in order to compute these quantities, you need to solve the topological string to high genus, and so far one can only do it to, in some examples, up to genus 50. And that provided evidence that this 5-dimensional black hole entropy does indeed scale as expected from the 5-dimensional Bekenstein-Hawking entropy. On the other hand, if you look back at this Donaldson-Thomas invariance, they appear, well, because they're related via this product formula, they don't have the same growth, and in fact, they seem to grow like e to the lambda square. So this is kind of it suggests the possible cancellations, which will play an important role later. So I have now described basically all the ingredients needed for this proof of the OSV formula, and I'm not going to tell you how you put them together. It should be rather clear from the way I described it. So at any rate, subject to several key assumptions, which is this split attractor flow conjecture, which I mentioned at the beginning. That is the finiteness of the number of multi-centered solutions for a given charge, a total charge, and moduli at infinity. Subject to this so-called extreme polar state conjecture, this is the fact that these states close to the unitarity bound can really be represented as bound states of 1 d6 and 1 d6 bar with sufficiently few d2 and d0s. And finally, subject to the possibility of neglecting so-called swing states, and those are states which jump once you try to interpolate between the lines of marginal stability and the infinite Kähler classes. So so they are quantified by some exponent denoted by xi. Then F and Moore have been able to prove an improved version of this OSV formula. That's for D0, zero total D6 range charge in the strict limit t equals I infinity with suitable cutoff on these infinite products. So this is really needed to give a meaning to these topological amplitudes. Up to an extra measure factor. And they have gained control on the corrections, which go like e to the minus p to the 3 minus xi of phi 0, which is the inverse of the topological coupling. So indeed, if this exponent xi is less than 2, then those effects are smaller than the Wirth instantons, and this OSV formula is meaningful. And moreover, the regime of coupling is also bounded by p to the kappa minus 3. I did not define kappa, but it has to do with the growth of the generacies at fixed ratio Q0 over Q0 max. So now what are those exponents? There is evidence that xi is equal to 1, and from supergravity reasoning, kappa is equal to 3, which means that OSV is vindicated for finite values of the topological coupling. Now, if we're lucky, and if kappa is less than 3, then maybe it will also hold for weak topological coupling, which was the original motivation. But the so-called entropy enigma, which is the fact that the multi-centered solutions seem to dominate over single-centered solutions for infinite values as you scale the charges to infinity. This entropy enigma suggests that OSV has to break down anyway at weak coupling, again, barring these miraculous constellations. So I'm not going to discuss this further. I think you should refer to the authors for any more details on these aspects. And in the last how many minutes? 10 minutes, I'll discuss this recent line of thought, which is to try and relate, try to count 4-dimensional black holes by studying instanton effects in 3 dimensions. Okay, so to lift some of the ambiguities of this OSV formula, it would be very desirable to be able to patch up those local degeneracies omega pqt into a globally well-defined object, which would be continuous everywhere, especially across the lines of marginal stability. Now, a good example to keep in mind is the chamber dependence of threshold corrections, which, as you know, have different instanton expansions, Wirth instanton expansions in different parts of the moduli space. But once you cross the Kähler walls, then they still conspire. They can be resummed and conspire to give the same result. So a natural candidate for such a well-defined object, which would receive contributions from BPS states, is the moduli space metric on the three-dimensional moduli space. After you compactify your supergravity on a circle of radius r, which is e to the u in my previous notation. So the structure of this compactification at the classical level is very well understood. The moduli space now becomes the product of two quaternary Kähler spaces, one from the hypermultiplets that were there already in 4 dimensions, but another one coming from the vector multiplets via the so-called C-map construction. That is, once you include together with the scalars the Wilson lines of the electric and magnetic gauge fields on the circle. A further important statement is that if you t-dualize along that circle, then you actually exchange the two factors. So as I said, the MV, let's say on the A side, is the C-map of the moduli space, vector moduli space in 4 dimensions. So it contains this vector moduli space, which is special Kähler, but it also has this circle direction as well as a torus. So it's a torus bundle over that space corresponding to the Wilson lines of the electric and magnetic fields. Sigma is the so-called twist potential, has to do with the Kaluza-Klein Wilson line. And in fact, this torus is a twisted torus. There is a non-trivial vibration of the sigma circle over the zeta twiddle base. Okay, so at finite radius, so this is the answer at large radius, but at finite radius, MV is going to receive instanton corrections from 4-dimensional black holes whose Euclidean word line winds around the circle. These instanton corrections will be proportional to e to the I p zeta plus q zeta twiddle. So you could disentangle, you could make Fourier analysis with respect to those directions to disentangle them. There are also extra contributions proportional to e to the I k sigma, having to do with states with non-zero nudge charge. But again, you can remove those by looking at the zero Fourier modes along this direction sigma. Now, by t-duality, these black hole corrections are mapped to d-instanton corrections to the hypermultiplet space in 3 dimensions. But because the radius is a vector, those are actually the same as the d-instanton corrections to the hypermultiplet moduli space in 4 dimensions, but now in type 2b on the same Calabi-Yau X. So this is a problem. So we're back to the problem of computing instanton corrections to hypermultiplet metrics in 4 dimensions, which has been on the table for 10 or 15 years, but hasn't been so much success yet because of lack of mathematical technology. So these coordinate Kähler metrics are difficult to describe. They're not described by just a single holomorphic function, but so our techniques have improved. The mathematicians knew it all the time, but we have started to understand what the mathematicians do. In particular, by the so-called superconformal quotient construction, the coordinate Kähler space are the same as hyperkähler spaces with a homothetic killing vector, so-called hyperkähler cones. And if you have a hyperkähler space, you can describe it by twister methods. In particular, you have 3 complex structures, and if you take omega 1 plus I omega 2, those are the omega I are the Kähler classes, then you get a holomorphic 2 form with respect to J3. So you have a holomorphic symplectic space, and so you can describe it by a so all the information is encoded in the structure of this holomorphic symplectic space. Now, by the Darboux theorem, any holomorphic space, any symplectic space locally is just trivial. You can use coordinates such that it goes like dp wedge dq, d mu I wedge d eta I here. But this is only a local construction, so you need to have such coordinates on various patches in your space. And all the non-trivial information is how do you glue those things together. Now you have to glue them by symplectomorphisms. In classical mechanics, there is a well-known way of doing this, which is to take a generating function of the initial position and final momenta. And this provides for you the most general symplectomorphism. And for special choices of these symplectomorphisms, namely if S is linear in the momenta plus a function of the position only, that means that the momenta are actually, the positions are globally well defined, they are the same on each patches. Then you recover the standard Legendre transform construction of hyperkähler metrics with isometries, so-called toric hyperkähler metrics, where this function h of eta plays the role of the generalized prepotential in the superspace, in projective superspace constructions of such metrics. Now we want hyperkähler cones, so we require superconformal invariance. And that fixes this function h to be quasi-homogeneous of degree 1, and, well, homogeneous of degree 1 and independent of this zeta, which was the coordinate on CP1, which determines which choice of complex structure that you make. So this has been made concrete for those moduli spaces in a large volume limit. So in the absence of instanton corrections, you can indeed describe the metric on this hypermultiplet moduli space just from the knowledge of the prepotential of MV. So the prepotential was degree 2. To make it degree 1, you need an extra variable, which is so-called superconformal compensator. We use this notation eta flat, which is maybe not the best thing we ever imagined, but anyway. This is the tree-level part, and there is also a one-loop correction which can be encoded in a very compact way. So the lesson is that there is a very compact way to encode hypermultiplet geometries so in the absence of instanton corrections. Now, once you include instantons, of course, you're going to break those isometries, and it's no longer so simple. So the generating functions are no longer so simple. So there's been recent progress in including a part of those instantons which do not break the one half of the isometries due to the work of Robles, Lanyard, Wojciech, Zoresic, Theis, and Doran. And this is doing the following. We know from the previous result the contribution of the worldsheet instantons. Those are the Gomov-Witten part in F. So by S duality, we can map worldsheet instantons to PQ string instantons in type 2B. And then we can map it back to type 2A into D0 and D2 brane contributions. And finally, we can use symplectic invariance to map D0, D2 to an arbitrary bound states of D0, D2, D4, D6. So the end result of this covariantization procedure is that to linear order, so at the one instanton level, you can write down this generating function of symplectomorphisms as just the same, this perturbative part, H pert, like here, plus an infinite sum of exponential corrections, again, going over the charges PQ of your instanton. Those are just plane waves on this torus, on this complexified torus. And here it's noteworthy that dilogarithm sums come up. They are the result of starting from the three logarithm sums of the Gomov-Witten kind of sum. So if you're familiar with the Kontsevich-Soberman formula, this should strike a chord. But if you're not, I'm just going to very quickly say a few words about this formula. So those people from mathematical discussion have proposed that across a line of marginal stability, there is an invariant quantity which, there is a quantity is invariant. This quantity is built out of formal group elements UPQ, which are themselves made out of Lie algebra elements EPQ, which satisfy the following Lie algebra. So this is essentially the Lie algebra of symplectomorphisms of a torus, except for this sign factor, which can actually be reabsorbed. So this formula, this dilogarithm formula here is very similar to the one we had in the previous formula. And so if you make the formal identifications that the instanton measure is the same as the black hole entropy, or at least the same as the as the invariance defined by Kontsevich and Soberman. And if you identify this symplectomorphisms EPQ with these linear functions on the space, and the bracket with the Poisson bracket, then you have a close connection to corrections on the hypermultiplet metric. So this is 0. Okay, good. So this has been supported in a very nice paper in the framework of gauge theories by Gayotto, Inaitsky, and Moore. And it's an interesting problem to push it to supergravity. I'm not going to say anything about it. So just a conclusion quickly. thanks to key physical insights, multi-centered solutions, 4D, 5D connections, large harmonic stability dualities, and to profound mathematics, much progress has been achieved towards precision counting of n equal to black holes, yet it's still far from complete. I think counting 4D black holes from instanton corrections in 3D is very promising. And in fact, it's not restricted to n equals 2. You could also think of doing it in n equals 4 and 8. I think this suggests new relations between Siegel modular forms and the forms of the corresponding duality groups. Irrespective of this line of thought, there are still many open problems having to do with counting black rings, understanding why F terms, only F terms contribute, understanding extremal non-BPS black holes, gauge supergravity, etc. So just to wrap up the talk, let me take the opportunity to congratulate Hiroshi, Andy, and Kumrun on their prize of the American Mathematical Society for the OSV conjecture and for providing such a marvelous illustration of the motto of the city of Paris, fluctuat nec mergitur, which means it is beaten by the waves, but it never sinks. Thank you.